So hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. First, I'd like to thank our members who have already joined the group, and I'd like to request us to invite more members by subscribing to our channel and also checking our comment section for various updates that we're getting, or rather also checking our description boxes for various links that we're going to put on similar content. So in this particular discussion, we're going to look at the concept of Gay-Lussac's law of combining volumes. And this is going to complement on the previous discussion we have had on the relationship between temperature, volume, and pressure. And of course, I'm going to put a link of those specific discussion in our description box. So this specific law of combining volumes was suggested, or rather developed by James Louis Gay-Lussac. And of course, we're going to see that from the specific concept of Gay-Lussac, we're going to have Avogadro's. So Amanda of God also give some aspect of these specific volumes, whereby we're going to see that there's a relationship between the Gay-Lussac's law and some of the, of course, inputs that was given by Amanda of Avogadro in trying to describe some of the behavior of these gases. Now, in contrast to the previous discussion we have had on various relationships, we're going to see that this is going to entail the concept of reactions of gaseous compounds. And of course, we're going to also to see that there's going to be a distinction between atoms and molecules, and where basically gases can be given in terms of molecular compounds, as we have been describing them in some of our videos. So in this case, the Gay-Lussac's law of combining volume states that when the temperature and pressure are kept constant, so I'm just going to give this one in summary form. So the law states that when the temperature and pressure of a particular volume of a gas are, of course, kept constant, the volume of a gas that is involved in chemical reactions are going to be in terms of ratios of small whole numbers. So in this case, if I give an example of or an illustration of a chemical reaction involving gases, perhaps this is going to shed more light for us on this specific law of a combining volume. So we're going to have nitrogen, molecular nitrogen reacting with the molecular hydrogen to form ammonia, and this of course is going to be given in terms of gaseous states. So these are two gases combining to form a gaseous product of ammonia given as such. So we can be able to give the reacting volumes in terms of so there's basically a unit of this particular molecule, but we're not going to include it, but I'm going to assume that we understand that from the stoichiometry of reactions, we understand that this is going to react in terms of ratios over 1 to 3, giving us a product of 2 units of ammonia given as such. So basically from Gay-Lussac's law, it states that when the temperature and pressure are constant, the volume of gases involved in a chemical reaction are in ratios of small whole numbers. Now, as we can see, these are basically integers, which are whole number integers given in that specific order. So basically for a gaseous kind of a chemical reaction, then therefore Gay-Lussac states that whenever temperature and pressure are held constant, the volumes which are reacting in this particular case are going to appear in small in ratios of small whole numbers given as such. So of course we're going to see later that this specific argument will be advanced by Avogadro, whereby Avogadro is going to suggest that the equal volumes of all gases at the same temperature and pressure contain the same number of molecules. Now, one of the characteristics of gases, as we said, that distinguishes them from liquids and solids, is that gases can be treated as I can roughly say, in an homogeneous way, in a sense that some of their properties are going to be given in terms of perhaps in volume, they're going to be or rather similar, in a sense that both of them, or rather for various range of gases, they can be compressed, they can be expanded, and of course, they can assume volumes of containers, and therefore we can have general properties for all of the gases. Now, in this particular case, for the concept of volume, we're going to see that, of course, equal volumes of gases at the same temperature and pressure are going to contain the same number of molecules. So in this particular case, I've mentioned the term of numbers, and I've talked about the concept of volume, and of course, talked about the concept of molecules. Now, in this case, from the general reaction that I've given on the board, I've said that a molecule of nitrogen is going to react with 3 molecules of hydrogen to form 2 molecules of ammonia. And this is going to be in terms of gases. Now, Amedeo Avogadro was the first scientist, of course, to distinguish between the concept of course, these atoms and the molecules, using this aspect of Gay-Lussac's observation, which I've said. And of course, Amedeo Avogadro showed that we can distinguish between these two aspects of atoms and the molecules. And as I've said, Amedeo Avogadro was the first scientist, of course, to distinguish between the two using Gay-Lussac's observation. And of course, this particular unit of a molecule formed the basis for gaseous elements, which of course are going to be made up of more than one atom. So basically, we are going to describe gases in forms of either diatomic or triatomic, etc. given in this specific case. For instance, I've given hydrogen and nitrogen being represented in this specific order, contrary to their atomic representation of nitrogen and hydrogen as such. So the difference between the two was given, was an idea that was advanced by Amedeo Avogadro, and therefore we're going to see that most of the gases are going to be assuming this diatomic or triatomic states as I've just given, or rather in this specific order as I've given that. So this is going to consist of 4 atoms, and of course that is going to range in that particular order. Now, for essence for us to understand is that this specific ratios of small numbers, which was advanced by Amedeo Avogadro, is going to give for us a basis of quantifying specific volumes of gases which are going to be involved in chemical reactions. And this, of course, is going to advance and develop into the concept of what we refer to as the mole, or the mole concept. And that is going to give us a relationship between reacting volumes of gases, and from there, then therefore, we can be able to quantify the various gases and find the relationship between those specific quantities, volumes, and their particular, perhaps molar masses as we go ahead. So I hope that this is comprehensive for us. And basically for the two, Gay-Lussac's law and Amedeo Avogadro, that specific relationship creates for us a basis for describing volumes and quantities, as I've said. Now, for essence for us is to remember of this particular concept that I've described in our last state, about the, of course, the basic unit or unit particles of gaseous elements, which are made up of this specific combination of atoms that we refer to as molecules. So catch us in our next video as we're going to look at an additional concept on this particular case of Avogadro's number, and the relationship between this particular discussion and that concept of Avogadro's number in our next video. So that is it for now, guys. Bye, God bless you. Catch us in our next video.